point in the plane is the intersection of two lines. So what we're talking about is here's two lines that go like these. They intersect somewhere, and so then that these determine a plane. So we could have a plane that would be like that from the intersecting lines, something of that kind. And so we're given the two lines in parametric form, and it doesn't really matter with a parameter whether you choose the letter T as your variable or choose to call it S, but in working a problem like this, it's handy to use different letters, because you see what you have to figure out is this point where the two lines will cross in order to get your point that's in your plane. And so using different letters for the parameters, you can say, well, where they cross, the x's are equal the y's, and of course the z's. So with two parameters, say you match where they're supposed to be at the x coordinate, so that'll get you one equation, t from this line L1 and 2s plus 2 from line L2 that are supposed to be at the same x. So if they are, they have to match. And then you can do the same with the y. If it's the same point with the same y coordinate, those have to match. So you can solve two equations and two unknowns, assuming the lines do cross. And then you confirm by seeing that the t and s values give you matching values for z. If they don't, then that would mean the lines don't actually cross, which is possible. You see, in space, you can have what people call skew lines like this. You can't say simply, anytime you have two lines in space that they're going to cross. They may do this, but if they do cross, there is a point at which the x and the y and the z will have to match. So you can take two of those three letters, x and y, x and z, y and z, and find what values for your parameters are required for those two to match, and then see if they'll check with your third point. If they won't, then the lines are skew and you can't do the problem. You know that since the problem's in the book, it's going to work, but you still don't know what the numbers are. So this is not very difficult algebra. Notice in this case, since this is plus t and that's minus, you can just simply add, and you get 2 and 3s and 5. And then you can solve for s, and after you solve for s, you can go back to either of these and get t. So if these lines are going to cross, it's when you think, if you want to think of your parameter as time, and what time is it? Well, it's time 0 on line L1, and it's time s equals minus 1 on line L2, where they're going through the same point, if they're going through it. So then take time 0 for z, and that gets you z equal 1. Take time s equal minus 1 for z over here, and that gets you 6 minus 5, which is 1. So they both go through z equal 1 then. which is what I'm talking about here. So my intersection point is 0, 2, 1. So now I have a point in the plane. If it's a plane that's defined again, we have these two lines that are meeting at 0, 2, 1, and at that point, that's also a point in the plane here. And so we now have our point in the plane, and we have more than that, because if we take the direction vectors for the two lines, we can cross them, and that'll get the normal. So the direction vectors then, so you're 1, minus 1, 1 for L1, and 2, 1, 5 for L2. So then we cross those in one order or the other, and this or 6, 3, minus 3, either way, would be your normal. Notice that 3 is a factor, so you could divide it out, still get the direction correct. So you could divide here by minus 3 and have 2, 1, minus 1, and use that for normal. You don't have to, it doesn't have to be a unit normal, and it can be longer or shorter, it just has to point right. So your general vector then is from the crossing point of the lines, 0, 2, 1, to x, y, z, and so you get this, and your equation of your plane is this dotted with your attitude numbers or anything proportional to them, you see. Because you're saying your dot product is 0, so you could divide here by minus 3, and 0 over minus 3 is still 0. So if you work this out, you get a thing like this, and now you could divide by minus 3, and so you could write your answer like that. Okay, I think that 28 is there in our maple. On the last back side of the next to the last page, and then on the last page. On the back side of the next to last page, you see problem 22, and you see again the normal line and the plane, and this with that display, problem 22. Again, I have the implicit plot, I have the plane 3x plus y plus c equal 5, and then I have the 3x plus y plus z equals 7. So I have the two planes. See, when we were doing 22 here, we started out, we wanted the plane where a given point was on the plane and it was parallel to this plane. And when we were doing this, you notice that what we came out with had the same attitude numbers because they were parallel, and the difference was in this being 7 and this being 5. And I was saying that these numbers relate to how far you are from the origin. They're not what the distance is, we'll get there yet, but they're related to it. So the difference, 7 minus 5, is related to how far apart planes are. So in 22, there actually are two parallel planes there from the commands, even though they're so close together, it doesn't really show. At least you can't see it easily, but there actually are two planes there that are very close together. And then this line that goes, uses the attitude numbers as its direction numbers. So it goes at right angles to both of them. Then with problem 28, you see I found the normals for the lines 1 and 2. I've used my direction numbers. I've used 1, minus 1, 1, and 2, 1, 5. And then I have used vector calculus to do my cross product. You see my N1 ampersand times N2 is the cross product. I could have typed cross prod also. So I got the cross product minus 6 minus 3, 3, which is what I put here. So I know I'm right because I got Maple to do it, okay? And if a computer says it, it must be so, right? And so anyway, my line 21 there, the numbers for the lines didn't print for some reason. You can see a parenthesis there. I don't know what happened, but anyway, the line, the cross product there gives the normal to the plane. And we find that the two lines intersect at 0, 2, 1 by going through solving simultaneous equations here. And we want the plane with the normal that's here, and this point 0, 2, 1 in the plane. And so we have the graph then. It's actually, the command for the graph is on one side of the last sheet of paper, the display, you see, and then on the other side, finally, you see the two lines. You see the red one and the black one, and then that plane. So they're crossing like my sticks, and then that plane is in the plane where those two lines are, well, segments are crossing. So you can use Maple and make drawings that go with these problems. So then let's talk about the distance from a point to a plane and from a point to a line. So if you have a plane like this with the three attitude numbers and this capital letter D is your dot product of the attitude vector or the normal vector and the vector from the origin to a point in the plane. It relates to the distance from the origin, but the actual formula is your absolute value here. This D could be a negative number. It's a number, it's not a vector, but it still could be negative. So this is the regular absolute value sign, and it's divided by the dot product of the attitude vector with itself. So it isn't just the magnitude of this number, it's the magnitude divided by the square root of the sum of the squares. So back here where we were talking about the two parallel planes, the distance from the origin to this one is 7 over square root of 9 plus 1 plus 1, square root of 11. And the distance from the origin to this one is 5 over the square root of 11. And so the distance between the two is 7 minus 5, which is 2 over square root of 11. So how far apart they are is not just this number minus that, but it's related to it. So you see they're not very far apart, 2 over the square root of 11. Okay, so that's why with the maple pictures, you really can't see that there's two planes there. For the purposes of my using maple, it's unfortunate that the problem didn't take planes that are further apart. Okay, so we have two handy distance formulas here. So point to line. So the point typically is not on the line. The other one is point to the plane, and typically the point is not on the plane. So by the distance, of course, you mean the shortest distance. So that's measured along a line that comes in at right angles. So if you have the line, it has a direction vector. We assume you know the coordinates of the point and you know the parametric or Cartesian form of the equation of the line. So then it turns out that the distance, this is the magnitude of a cross product. You get the direction vector for the line cross with P0, P1. Okay, now P1 is your given point, and P0 can be any point on the line. It wouldn't matter what point you take. You just have to figure out a point on the line and see what you're doing. Here's your point you're given, and here's your line you're given. And what you want is the distance in green here, the D. So you get any convenient point on the line, no matter what. And then you can get this vector, which you call P0, P1. And what you want, you see, would be this side of the right triangle. So it would be the length of this times the sine, because it's the side opposite. So what I have here. So what I do is I multiply top and bottom by the length of L, and that's legal because it's a number and not 0. And notice what you have on top now is the magnitude of the cross product. So your formula is magnitude of the cross product, the L vector for your line, and any point on the line to the given point, making this other vector, divided by the length of the L vector. Then for point to plane, you have the plane here, and you have to know its formula. And you have a point off the plane up here. You have to know its coordinates. You find any point in the plane that's convenient. And you can think of it at the foot then of your attitude vector, your normal, because again, that normal is not just one arrow, it's infinitely many arrows, so you can get one up that'll have its tail at wherever you are in your plane. So what you want then for your distance, you see, is the component like this. I've drawn this over here where the point is. So this would be here like this, and then what I'm doing is coming in here. So I'm saying that the distance down to the plane, thumb to finger, is the same as that distance. Two sides of the rectangle. So if I know this, then this orange length cosine is this side or that side, say. So that's P0, P1 cosine. So then I multiply and divide by the length of the n, which I know if I know the equation of the plane. And then the numerator is the magnitude of the dot product. Notice that this is not a vector, so it's not the norm of a vector, but it's a number that could be negative. If your angle is more than 90 degrees, your cosine is actually negative. So distance is never negative. So if you have a problem and you do your dot product and you get a negative number, don't use that negative in your answer for the distance. Take the absolute value. On the test, if you give me a negative number for a distance from a point to a plane, I'll take a point off, because you should know that distance isn't negative, as long as you're using Euclidean geometry anyway. So over here then, I've repeated the two recipes because I'm standing over here and I don't have sufficient brain power in my declining years to remember a recipe from that panel of the board to this panel, right? I'm like all the aging politicians that can't keep their lives straight. So anyhow, well, if you told as many as most of those people do, you couldn't keep them straight either, even young and bright as you are. So anyhow, for a plane, first of all, what I'm talking about is the general formula for the distance from the plane to the origin. So say you had this plane, and the point off of the plane is the origin. And so I'm looking at my formula here in that special case. So a point that would work, remember you have to get a point on your plane. So d over a for x, 0, 0, the a's would cancel and you'd get d equals d. So here's a point that works on the plane. And then you take your vector from it to the origin. So you have 0 minus that, 0 minus that, 0 minus that. So here's your vector, and that would be your P0, P1, and then your n is A, B, C. So you do your dot product, and I see I lost one side here. And now you do your dot product and divide by the sum of, well, your length of n. And you see that what you get, the a's cancel, and then you have 0 and 0. So you have your magnitude or absolute value of minus d. So I don't really need the double thing here. And so your distance from the origin is the absolute value of the d number over the square root of the sum of the squares. So that's a handy thing to know. And then look at the couple homework problems. So this is a line that's given and a point that's off the line. So that's going to be this formula. And so you have to find a point on your line. So for instance, at t equals 0, you'd have 0, 1, 0 on the line. And this is your point you're starting with. So your P0 to P1 vector is these numbers minus these. 2 minus 0, 1 minus 1, and minus 1 minus 0. So then you cross those, and you get your distance formula is your magnitude of your cross product divided by the length of the L vector, and your cross product is 2 minus 6, 4, and your length here, you see you have 4 plus 4 plus 4 is 12, and square root of 4, square root of 3. So you get a number. And then if you look at problem 42, you have a point and you have a plane, and a point that's in the plane would be 2, 0, 0, because then you get 2 times 2 is 4. So point in the plane then, 2, P1, you have 2 minus 2, 2 minus 0, 3 minus 0. So you have this vector and dot with the n from here, 2, 1, 2. And that dot product is 8. See, 0, 2, 6. And then your length here is length of square root 9. So your distance is 8/3. So remember now, distance is never negative. One other type of problem that you can do with these methods is this. Say you have a line that's in parametric form, something like this. Then if you think of your parameter as like time, so that as t varies, as time varies, you go from point to point to point on your line, you could ask yourself a question like this. For your line in parametric form, suppose it crosses a plane that's given like this. What time is it when it would cross the plane? What would you do? I know the equation of the plane, so I know the A, B, C, and D. And I know the equation of the line, so I know little a, little b, little c, and x0, y0, z0. So how would you figure out what the t value is as you move on this line? What's the t value when it hits the plane? What would you do? Who wants to recite?
I have an idea, but I don't want to say what it is.
Well,
I'm not sure. I'm not sure which one it is actually.
Well, what is your idea? What would you do?
Well, I was thinking, take the differential.
No, you don't want to take a differential.
Okay, we'll see. That's what I didn't say.
Okay, that's all right. At least I got you to say something. So who else wants to say something?
Would you use a formula to find the perpendicular?
No, you don't know that it's coming in perpendicular.
Okay.
See, say the tabletop here is my plane, and I could be coming in on a line at any angle. So the angle here isn't part of the issue. I'm moving along this line, according to these formulas as time varies. And my question is, what time is it when I'm hit here? And we have a way to figure that out. And then after we figure out what time it is, we can go back to here and figure out the coordinates of the point. Yeah.
Is it just a guess because you use t as a variable over here?
Yes, exactly. That is your variable.
Yeah, do you solve for
See,
t with the...
Yeah. Take your formula for x, which is here, plug it there. Your formula for y, which is here, plug it there.
Oh, okay.
Your formula for z, which is here, plug it there.
Oh, okay.
Now what you have is t down in here is the only variable. See, what you'll have looks like this. Not one, B. So the only thing that's an unknown now is the t, so you can solve. You know all these numbers. So now you can solve for t, so that's what time it is when moving along the stick I've reached the tabletop. And then if I want to know the coordinates of the point where I reach the tabletop, I can put that t back here and there and get the x, y, z. So you can do a problem of this sort. You'll find there is such a thing on your test. See, I'm teaching the test. Okay. So that's a little different problem from those that are in the book, but you do have the tools to do it once you see it. Everything with math is a once you see it, it's easy sort of thing, right? So, anyway, I guess I will wish you a happy Labor Day weekend. And so problems 21 through 26 want the equations of the plane, where the normal to the plane is capital letters A, B, C. Remember that for my direction vector and my direction numbers for a line, I'm using small letters, and for my attitude numbers, as we are calling them for the plane, I use the corresponding capital letters. And this is what your book is doing. This is fairly standard. So a general vector in the plane, again, in order to specify which plane it is between parallel planes, you have to know a point in the plane. Between parallel lines, to specify, you have to know a point on your line. Between parallel planes, you'd have to know a point on the plane. And then parallel planes would have the same attitude numbers. So we suppose x0, y0, z0 is a point in the plane. And then a general vector in the plane is from that given point to a general point x, y, z. And so it's perpendicular to the normal, so the dot product then is 0. So that specifies the equation of your plane, where your normal is the vector A, B, C, and the G is X minus X0 and so on. So you write out this dot product. So you have A times X, B times Y, C times Z, and then minus AX0, BY0, and CZ0. And then you can move this across. This is a number, after all, for any particular plane, and call it D. And then you call the coefficients here of X, Y, Z the attitude numbers, and they're the components of the normal to the plane. And then the D is this dot product of a vector from the origin to the given point in the plane times the normal. You see, this sum of products, A, X0, B, Y0, is like a dot product of this vector with the position vector for your plane, which is the vector from the origin to the point that you're given that's in the plane. So you can look at this that way if you want to, or just simply that it's a number. So something that looks like this, where A, B, C, and D are constants, and the X, Y, and Z are first power, the graph is a plane in space, three-dimensional space. So then we come over here. So look at problem 22. It wants the equation of the plane, and you're given the one point that's on the plane, and it's parallel to this other surface. Now, from what I just finished saying, you know that this surface is a plane. Plane, it's always a plane if the X, Y, and Z are first power and in separate terms, and everything else is a number. Okay, so the attitude numbers for this plane are 3, 1, 1. In other words, the normal is the vector, 3, 1, 1. So if it's parallel, those are, this other plane, P, is going to have the same normal, another member of the infinite set of arrows called 3, 1, 1. Remember, there's an arrow every place you want. So that, what we had the first day of class, this concept that the vector is an infinite set of arrows, gives you an arrow anywhere you want one, and it's really key to the whole works here. That it's a subtle sort of thing, and people can go a long way, say, in physics and engineering and in school generally, and never quite really get how subtle this vector concept really is. So anyway, n for the plane in our problem is also 3, 1, 1, and we want the equation where this point is on the plane and this is the normal. So if you want to write it out as a dot product, then x minus the x coordinate, y minus the y coordinate, z minus the z coordinate of the point that you're given, dotted with the normal equals 0. That's always your basically defining equation. And so then if you work this out, what you get, you see, is the same on the left. They're parallel, so they have the same normal, so they have the same coefficients on x, y, and z. And the difference is in the d value. This d value, which is this dot product that I pointed to over here, right here, this dot product of the normal and the position vector from the origin, that's not the distance. That number doesn't equal the distance to the origin, but it's related to it, and we'll see what the relationship is. It's on the board there. So essentially the difference between these two planes is in the distances from the origin. And then we can use these two numbers to get the distance between the planes. We're not quite there yet, but we'll get there. Meanwhile, take a look at 23, which wants the plane that contains 3 points, P, Q, and S. Don't ask me why they did P, Q, and S and not P, Q, and R. I didn't write the book. Discrimination against the R's. Okay, R's of the world arise. So, you can get two vectors from the 3 points, P to Q, say, and P to S. And then you take their cross product, if they're not parallel, and get the normal. Because the cross product of two vectors is a third vector that's perpendicular to the plane of the two you're crossing. We had that yesterday, right? You have A and B. A cross B is a new vector, and in general perpendicular to the plane of A and B. So that's my game here. So P to Q then. You take the Q numbers minus the P numbers. You get this vector. P to S. You take the S numbers minus the P numbers, like I have here. You get this vector. Then you cross them. And this is what you'll get if I did it right. And so that would be something you could use for the normal, or really, of course, you could use anything proportional to it. You could, of course, have done your cross product in the other order, PS cross PQ, and then from yesterday's class, you should remember this would then be minus, plus, and plus. You reverse the order of the cross product, you reverse the signs. Wouldn't matter as far as working the problem. So any vector from the given point, say take any one of these is your given point. So for instance, if I take the Q, any vector from Q to X, Y, Z is going to be perpendicular to the vector made of the attitude numbers. So X minus 2, Y minus 0, Z minus 2, dot, the normal would be 0, and you can grind that down, do your algebra, and you get something like that. Okay. Let's look at a little maple, and then we'll come back and do some more of this. So, drag out your maple, getting here without. There's an honest man. Dylan has got here without maple.
Yeah, it's somewhere.
So we turn a couple of pages and get to these problems. So I'm on the back side of the second sheet of paper as the thing is stapled together. And you recognize problem 1, which is down here, where the L vector is the 1, 1, 1, and the point was 3 minus 4 minus 1. So if you want Maple to draw such a thing, you use the command space curve, which applies whether it's a line or what you ordinarily think of as a curve, where the curvature is changing. And so then you have to take what you got for the equation of your line, say 3 plus t minus 4 plus t minus 1 plus t as your vector x, y, z. So you see I'm using the brackets for my vector, and I have my 3 components there, and then you have to decide what limits you want to put on t. Depending on what limits you take, you'll get a longer line or a shorter one. And so you do a little bit of experimenting if you, with your choice of t, the limits on t if you're trying to make a nice picture. And I did minus 20 to 20 and chose a color, red, so that you could see the line as opposed to the boxed axes. So color equals red, axes equal boxed. Thickness, you can make your curve thicker or less so with thickness equal. The bigger the number you choose for thickness, the more ink will spray on the paper, supposedly. And you can put a title on or not. So then you see the boxed axes and you see the line. So this one, you see your direction vector for the thing is 1, 1, 1. So you're coming up from the origin to the point, say 1, 1, 1, in specifying the direction vector. So you see something then that's coming up from the, it's coming up at the angle that the red line shows. Then for problem 2, you look for space curve. Again, you had to work the problem as we did here to get the x, y, and z, which are right in here. And so those go in the vector. And this time the color's green. And again, what you have is a line graph, of course, and so it shows as a diagonal in your boxed axes. Then with the problem 8, which we also did, this is the one where we're told that the line is perpendicular to a plane, and we have the actual line over here, I guess. Don't we? Where did it go? Well, let's see. I thought we did 8, didn't we? 2. Well, I guess maybe I didn't. Well, anyway. So, what I've done here, if you look at the maple in problem 8, I have display. Now, you type display, when you have more than one plot structure that you want to show in the picture. So you see what I'm showing in display, I have the equation of the plane, 3x plus 7y minus 5z equals 21. And if you define a surface with an equation, as opposed to when you use space curve, like problems 1 and 2, and you introduce the parameter as your variable, that's defining like a function. X is, Y is, Z is this function of t. So then you're using plot, only instead of calling it plot, you say space curve. When you define a surface, say, by an equation, like the equation of this plane in problem 8, then you type implicit plot, and you have then to give limits on each of the variables that you named. So in your equation, you've named the variables x, y, z, so you have to have limits on x, y, and z, which you see I have. And then I have the line that's using the attitude numbers of the plane as its direction numbers. And so that's space curve then, that line, and that's in the brackets, and then the thickness. And you see I have the line and the plane on the next page. So the red line looks believably like it's directed along the perpendicular to the plane, I think. So that's what this is trying to show. So here's problem 8. I was sure that we had done it. Starts right here. So problem 8 again wants
Sure
the
does.
line when this point is on the line and it's perpendicular to this plane. So the 3, 7 minus 5 then would be the vector that would be directed along the red line in the maple drawing. That's the attitude numbers for the plane. And then we have our line here. So our line is the space curve that I've used, 2 plus 3t and so on. And our plane up here is the structure that's defined by an equation. And so you use implicit plot for this. And here where it's x equal y equal z equal, that's like function. So it would be like you use plot, only when it's in 3 dimensions and it's a curve, the plot command becomes space curve. And it would work even if these were not linear. It wouldn't be a line then, but it would be a curve, and it's how you draw the curve. Okay, so let's do some more of the problems, and then we can look some more at the maple. So I think we did this one. I think we're ready to do 25. Is that right? Don't let me waste time and repeat something I already did, but I think this is where we picked up.
Yep.
Okay. So we have a point, and we want to know where the line which we have here is the normal to this plane. So P is the plane, this is a point on the plane, and then we want where the line is normal to it. So N for the plane is the same as the direction L for our line, if our line is normal to the plane. That's the same concept that we've used here with problem 8. So that means then, if you look at your line, your L vector, the components are made from the coefficients of t, so they're 1, 3, 4. So if this line is also the normal to the plane, that means that the normal vector for the plane is also going to use 1, 3, and 4 for its attitude numbers. In other words, I'm using 1, 3, and 4 as small letters A, B, C for the line, and big letters A, B, C for the plane. And so we have then that the general vector in the plane is from the point 2, 4, 5 to X and Y and Z respectively, and then the dot product of that with the attitude numbers, the vector made from those would be 0, and so we dot that out and we get this plane. Well, we'll look at 28 in a second. These lines now can be in a plane or they can be in 3 dimensions. So the general setup is for 3 dimensions. So think of an origin over here somewhere, and you have a vector that I'm calling R0, the tip of which is a point on the line. This doesn't necessarily have to be any particular angle in here. The way I've drawn it, it looks as if it's maybe coming in perpendicular, but that isn't necessarily so. That's just how I drew it. But in order to specify a line in space, it's the same as in geometry in school. You have to know a point on the line, because if you don't know a point on the line, you can't tell which of 2 parallel lines it is. And you have to know slope if it's plane geometry, and you have to know the equivalent to slope in 3 dimensions, which is essentially you have what we call a direction vector, which in this drawing is in the brown color, and I'm calling it L. Okay, so the equivalent then to knowing the slope, yeah.
Is that red line?
That's an R.
Is it R1 or just?
Yeah, since the word subscripts there are ones, you're right. Then that's R1.
That's what I thought.
Good for you. And I put my, okay. 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 That's one for your side. Did I spell your name right?
You did actually.
Yeah. Well, anyway, so if you know 2 points like this, specified by R0 and R1, then the third side of your triangle will get you the difference, R1 minus R0, which is the direction vector, or just simply the direction. The numbers, which are the components of that, A, B, and C, are called direction numbers. There isn't any great reason you have to memorize the terminology, but they do have a name. You call them the direction numbers. And if you think of this L vector, remember a vector, once you have a representative, there's an arrow everywhere. So there's an arrow that's like L, another member of the set, with its tail in here that you could imagine. If you thought of the L vector over here, then you'd have the angles with the x-axis, y-axis, z-axis, and those are called the direction angles. And it turns out that the sum of the squares of the cosines of those angles is 1. That's all in the book. You don't necessarily need to know it, but I'll at least point it out. So your problem may simply give you the L vector by giving you the direction numbers for the line or the direction cosines, or if not, the problem may give you 2 points, x0, y0, z0, and x1, y1, z1, and then you can do the third side of the triangle and get the direction vector. One way or another, either you're given the direction vector specifically or enough information, say 2 points on the line, to get it. And that's the equivalent of knowing or being able to get the slope if you're back in the plane. So then you have either one of these points and your direction vector. So then you can say this. Say you're thinking of this point. You have to know at least one point. Say you're given this point, then the vector from it to any general x, y, z. Now these are not subscripted, those are commas. Then that's a parameter t times your direction vector. In other words, the brown vector is parallel to a vector from here to any point x, y, z. The blue one. The blue one then is parallel to the brown one, and the t is your constant, if you like, of proportionality in parallel vectors. You call that sort of thing a parameter. So then you can match up components, because this minus this gives you the vector x minus x0, y minus y0, z minus z0. So then x minus x0 is a t, and so on like that. So you call this, see, I've written it down here, you call this the parametric form of the equation of the line. The t is your parameter, as it's called, and then the a, b, and c are the direction numbers, so they're like the three of them together defining this vector, define the slope, and the x0, y0, z0 is the 1 point at least that you have to be given. So then in that sense, the x1 minus x0 is the a, the y1 minus y0 is the b, and this is the c if you're given 2 points, which will define a line. So then you call this the parametric form, and Then if you wanted to rewrite this without the parameter, you can do the algebra that I have here. When you say Cartesian in this class anyway, or a class like this, you mean the equation of your line or curve or surface, whatever it is written without a parameter. It's just using the x, y, z coordinates. So you see, you could write this way, x minus x0 over a is t, y minus y0 over b is t, z minus z0 over c is t. So without going on to say equals t, if you just stop here, you have an equation for your line involving the direction numbers and a point on the line. And some people call that Cartesian form, and some people call that symmetric form. I don't think that you see symmetric in your book, but when I took the equivalent of this class so long ago, that's what we called it. And of course, this is assuming the A, B, and C are not zero. You might have something where, say, for instance, the C might be zero. If the C were zero, then this would simply say Z is some constant. In that case, your Cartesian form would be this equal that, and then comma, Z equals the constant I'm calling Z0. So you could have a thing like that too. Okay, so look at problem 1. So you're given the direction vector and you're given the point. So remember, this is only problem 1, so this one is comparatively easy. You're just back to here to plug in, you see, because if this is the point on the line, then this one is x minus 3 from there equals the a, which is the 1. So this one gives you the x minus 3 is t. This one gives you the x minus a minus 4, so plus is t. And this one here gives you the z minus a minus 1 is t. So you can write it that way, or you can solve for x, for y, and for z. There's nothing wrong with this answer. This is more what the book actually does. They go ahead and move the number across. That's just whose book you're in and whose class you're in. I don't care about things like that. Although my math lab would be one way or the other, whichever it is, and it would be bound and determined you must have it that way. Okay. Can't argue with computers ever, right? Can't understand them or argue with them. So, problem 2. So now you're given 2 points. So that's the equivalent of, say, my picture here, P and Q. So then getting what's in brown here is from, say, P to Q. So you know how to do that. We've practiced that. You take this number minus that, this number minus that, this number minus that one. Okay. And then you can use either one of these points. And so using this one, then my blue vector, say from here to some x, y, z, would be x minus this, y minus that one, z minus that one, and that's equal to your parameter t times this direction vector. And then match up the components and solve for x, y, z. Okay, so look at problem 8. That wants the L vector, well, the line rather, the script letter L is the line, the capital letter L is the vector. When you know a point on the line, say that's like your point P, and you're told this, that your line is perpendicular to some plane. Okay, well, that gets you the L vector because it turns out, and when we get over there under the clock is where I show you how we get this for a plane. If you have a plane like this, the coefficients of the variables x, y, z, in other words, for this plane, the vector 3, 7, minus 5 gives you the normal for the plane, and your line is perpendicular to the plane, so that means in turn that the direction vector for your line would be the normal vector for the plane, or anything proportional to it. So I haven't really addressed the issue of how I know from the equation of a plane to take the coefficients of x, y, z for the normal. Talk about that in a minute over there under the clock. But supposing that you trust me for that long, I won't be out of your sight, you see. Then we get the L vector from the numbers here for the plane. These numbers, by the way, have a name. They're called the attitude numbers. Attitude, like if you're thinking of an atomic-powered submarine that can maneuver in 3 dimensions, it can be going through the water and it can be tilted somewhat, or talk about flying airplanes or spacecraft. The attitude of the thing would be how it's pointed as it's going through space. You have the same concept actually with the front end of a car, because if you take it into an alignment shop, there's camber and there's caster and there's toe in, right, for the front wheels. And the caster in the suspension of the front wheel is whether it's thrust forward a little bit or backward a little bit, and the camber is the tilt of the wheel side to side. Like if you think of 2-lane roads that are kind of got the hump in them for the water to drain, that's camber. And then toe in is walking like this, kind of pigeon-toed. Okay, so you take the attitude numbers for a plane, that's the normal to the thing, and if the line is perpendicular to the plane, then they are also the direction numbers. So then what I have is the given point, 2, 4, 5, and these are the given direction numbers. So x minus the x coordinate and so on, that vector is t times this L vector from here, and then you write the equation. So then there are some questions that want you to parameterize a line segment. Well, the difference is that in these problems, the t can take any value as you extend indefinitely far on your line. if you have a line segment, it starts at one point and ends at another point. So then your t will be limited in value, and you trace out the points from start to finish, say hand to hand, as t runs typically from 0 to 1. So typically at t equals 0, you're starting here at the left, and t equals 1, you're finishing up here, and this is your line segment. So you say you're thinking of this as your beginning point, so you have x minus x0, y0, z0 is your parameter, then times x1 minus x0, the second point minus the first one, that's getting you the direction numbers. So then when t is 0, you're back here at x equal x0, y equal y0, and so on. That'd be like the left hand. And t equal 1 then, you're at x1, y1, z1. So for example, problem 15, if you want to parameterize the line segment from 1, 0, 0 to 1, 1, 0, then start here, so you have x minus 1 and so on, is t, and then the direction vector would be these numbers minus these, which is here. So this is, your A is 0, your B is 1, your C is 0. So you have 0, 1, 0 here. So x minus 1 is 0. In other words, x is 1. Y is t. See, y equals 1 times t, where t goes from 0 to 1, and z again is 0. So your parameterization would give you just the line segment. X is always 1, y is what varies really, and z is always 0 for that. So here's